In this video number 16 in the Foundations of the Computational Economics course, we'll be talking about visualization of data and solutions for the economic models. Let me start by saying that I'm a huge fan of visualizations. Why do we do that? Well, the main point is that whatever you do, whether you become an academic or you go to the industry work, conveying ideas to others, conveying your ideas to others, is extremely important. Ability to efficiently explain what you came up with to other people may be crucially important for the success of your career, wherever you are. And I find that visual tools, the visual props, is probably one of the easiest way to explain what you're doing to other people, especially if you're doing a lot of math. Now, graphics are also very important and very useful for checking your own work. You can debug using, you can find errors in your code using graphics and plots. You can check whether your model has created some new knowledge by looking at the visualization of the simulations from these models. You can verify that what you found is really a result of something new and not just a simple error in your code. And then, of course, aggregating large amounts of information makes it possible to get a bigger picture and get a bigger message by looking at the graphs, at the plots and visualization of different types. So here's an example. Do you know what this is? Take a guess and then think about what that tells you about the differences pictured here. And well, let me give you 10 seconds. Well, maybe you've heard about this before. This is a part of the global heat map that generalizes all the data on trainings uploaded to the Strava.com website. And what we're looking at is the North and South Korean. Think about how much data is aggregated in this single picture, and think about the big message that this picture conveys. Well, if we think about the tools that we're using for visualization of data and also solutions of the numerically solved models, well, Matlablib is the library that we've used so many times already that I have to put it here and talk a little bit about the general ways to use it. But there are other libraries as well. For example, Seaborn creates a very beautiful graph, so Bokeh, which is the tool to create interactive plots. Now, I thought that I would go through the details of Matlablib, and I've decided against it. Well, first of all, there is a very good tutorial that I decided to make compulsory for everybody to follow. And frankly, the way I work with Matlablib is usually I just go to this gallery of Matlablib examples, and I sort of scroll until I see the graph that I want to create myself. And then every of these examples comes with a code, which is fairly easy to understand, right? Especially using the examples from the lectures that we already saw. So, for example, here, I want to create a line that looks something like that. I just have to find the proper code lines that specify the line properties the way I want. And I copy, particular parts into my code. Spline demos, right? Look at the axis here. The axes are, the ticks are done in a particular way with particular labels. You can see how it's done in this code. So really, every time it's by example that I work with the Matlablib. Here's an example of multiple plots in the same picture in different scales of the axis. And you can see here that, to create a log axis, all you have to do is to call a particular method of the object x. And so the background is that the plot is a collection of graphical objects of different sorts, axes, lines, shapes, and areas, and we manipulate the properties of these objects, call their methods in order to achieve the graphical picture that we want. So instead of going through the details of how to do this or that particular graph, let me concentrate on this 2 points. Well, 1 point rather. I will spend the time in this video to show you the examples of the graphics that I use in my own research projects, different research projects that I'm working on. And then there will be a link to a compulsory online learning resource that you'll have to follow. So types of plots, there are many different types, and it's important to choose the type which fits the situation that you want to visualize. You know, bar plots, scatter plots, lines, areas, pies, and especially interesting Sankey plots, which is excellent for visualizing flow diagrams. It's important to think about what you want to do with the visualization, what kind of message that you want this graphics to convey, what types of variables, you know, number of variables to be represented. What are these variables? Are they continuous, categorical, or maybe ordered? All of these factors should inform your decision about the use of a particular graphical tool. So here are the general tips. Less visual clutter. The information that you show should consist of the elements such that every element has some meaning to its existence. And we'll see what I mean just in a second. It's very helpful to read the manuals. So I said that I do it by, you know, I create graphics by example, but then once you see the example code and you don't quite understand it, it's very worthwhile going into the manual and checking what arguments different methods take, because it turns out that the default arguments are not the best in many situations. I would say you should be quite careful with 3D plots. They are much harder to make clear and you know, support the message that you want to support. And on the other hand, you know, animations or sequences of graphics that are changed by, you know, flicking the slides, for example, is something to look at. And I found animations or just straight videos very helpful in some of the projects. So here's an example of less visual clutter. So I want to show that a particular function, this happened to be value functions in a dynamic problem that we consider. They have what we call a primary and secondary kink. You know, I don't care about what units are on the axis. So the axis don't have any tick marks. It's just that generally on the horizontal we have assets and the choice discrete choice specific value functions on the vertical. And I just want to highlight that there are these kinks. You know, the kink which is created by the intersection point between the green line and the blue line, and then the blue line also has a kink in itself. This is all I want to say. This is what this illustration is doing, and therefore there's no other information on this plot. Let's talk about the choice of an appropriate plot type. Here's a plot where we are trying to answer a question whether a particular algorithm has a polynomial or exponential runtime, something that we talked about earlier. The algorithm's runtimes as measured are plotted with dots, right? Because we don't have any particular functional form on them, or these are just individual trials, and therefore dots is a very good way to show these as unconnected. And now we're looking for a particular pattern in these dots, and we're fitting different lines. Now remember that to tell whether an algorithm is exponential or polynomial, you have to plot it with the vertical CPU time on the log scale, and then see whether you have a line or you know, a straight line or some curve that appears. And we are fitting the curve to the red dots, and it's clearly not a straight line. Whereas for the black dots, it's possible that the black line is the one that describes the pattern better than the blue line here. And therefore, we're also matching the color of the line and the dots in that case. We're arguing that this is more like a straight line. Here's a combination of plots, and in terms of the dropping the visual clutter, this is not the best example, but here the idea of this plot is that we have some data observed in different ages for people, and this data, well, it's superannuation amount, is drawn in lines, and lines are used because this is across life, right? Every point is connected to the value of that point of the previous year. But in the same time, the superimposed is this bar chart. The bar chart shows how many observations we have at particular age in the data. This comes from Hilda data, by the way. Now, the total number of observations is one thing, and another is the number of observations which are not missing. And unfortunately, for this particular variable, there's a lot of missing information, missing observations. And the fraction of non-missing observations is shown in the second sort of dimension of the bar chart at the bottom with this field. You can see the fraction of non-missing in all the data that we have. The gray area, this combination of a line and a shade or aerial plot, allows you to see how precise these observations are. The lines show the median and the mean less top 15%, as it says in the legend, and the gray area shows the variability of this central tendency plotted. Here in this graph, we are trying to bring two distributions together, and then of course a histogram is a good tool to show it, but overlaying two different histograms creates sort of a visual mess, and therefore we're just using the outline of histogram for the data, observed data and the simulated data, and if these lines are close to each other, then the whole distribution matches up. That's the idea behind this plot. And this is called the staircase type line, where the stairs, where the observation, each data points are connected, but they are not connected with straight lines, they're connected with the steps. Now, the aerial plot is ideal in the situations where you want to show the change of composition of something along a timeline or along some other variable. So this is the composition of the gasoline in Denmark, and you can see how what are the fractions of different taxes inside of the price for gasoline and how that develops on a time scale from 1990s to 2010s. So area plot is a very suitable plot type here. Now, here's finally a 3D plot. This comes from the project where we modeled the car purchases in Denmark. And here the vertical axis tells you the number of cars of a particular car age on this y-axis, I suppose. And then the x-axis has calendar years. Now, the feature here, and this is what the main text is talking about, in this plot, we want to show the waves in the distribution of cars that travel through time. So if you think of a particular time, say 1995, and you slice this plot along the, along with a surface with a plane that passes through 1995, then you will see a distribution of cars of certain ages in the economy. And you can see that around this time, 96, 97, the economy was in boom. So there was a lot of new cars around. And then there was this valley in the distribution, and then some more cars of an age of around 10 years. Well, what happens as time goes by? So time goes from 95 to 2010. The new cars which were bought in the good times of the economic boom, they start aging, but they don't disappear, right? They sort of stay around in the distribution. And you have this ridge, the diagonal ridge that travels in the distribution of cars along the time diagonal as cars age. And so this additional ridge that we see over here, that's the end of the ridge created by previous economic boom sometime in the late 80s. And you can see this reach sort of dies out. These are accidents and scrappage. Old cars are being scrapped. The cars in this reach are already over 10 years old. And by the time they're about 15, 20, then there are not many cars which are left. And so here it was impossible, more or less, to show these waves in the distribution without the 3D plot. And yet we had some troubles of how to align it such that the waves, which is the main feature of the data that we want to show here, are clearly visible. And therefore, time runs in some strange directions and so forth. Another way to do it was to show in the animation that I've mentioned how the distribution changes year to year, and we've done that in some presentations as well. Now, maps is of course a very good example of particular graphics which fit the projects dealing with geographical distributions. This is a map of Denmark. And we're talking in this project about how people choose locations. And so we're plotting everything on maps in this particular example. And so here is the Sankey plot that I mentioned before. This is the visualization of the flows in an experiment that we ran in one other project, which had some tests before the experiment began. Then it had a learning stage, and then it had a debriefing stage, the third stage. And you can see how the respondents were tested on their knowledge of some financial products before they came to the experiment, and then during the learning stage, you can see that a lot of those who answered the questions incorrectly initially learned how to what are the correct answers and transferred into this sort of the people who know. And interestingly, some people who seemed to know in the beginning, they answered the learning stage questions incorrectly, but then gone back. And also some people who knew, there's 14 people in the middle here, they somehow didn't answer the final questions correctly. So this is a really nice way and quite intuitive, in my view, way to show how different flows through this three-stage system occurred. Now, sometimes you have to use statistical plots. So this is the plot of the CDF of all of the equilibria in a particular dynamic game that we're solving. You can see that there are many equilibria here. What's it, 14 million? And we're measuring, for each equilibrium, we're measuring how efficient it is, with one being fully efficient on the horizontal axis, and then the fraction of the equilibria which have particular efficiency measure is plotted on the vertical axis like a CDF would have. So this is an empirical CDF plots. And you can see that what we want to say is that among all equilibria, a lot of them are actually more than 30% are fully efficient. But if you look at the particular types of equilibria, you can see how the green line and the red line join the one before reaching the full efficiency here, which means that these equilibria cannot be fully efficient, even though some of them are pretty close. All right, so here's another note, which is to say that choosing the right type of the plot, when choosing the right type of the plot, we also should consider how much information can be represented by a particular plot. And just sort of from the theoretical point of view, what are the channels of representing information that we are operating with? Well, let's start locations of different graphical objects on the axis. X and Y, obviously in the 3D plots there's Z as well. Then we can use different colors. We can use different line and marker styles. We can use different size of the graphical objects. We can use animations, as I've mentioned before. Finally, you can think of putting many plots in the same figure to represent some additional dimension of the data. So here's an example of a combination of all these different dimensions in one picture. We have 2D plots, so each dot is located in a particular spot. What's plotted here is from the same paper, actually, where we're calculating this mini equilibria of a particular dynamic game. Each dot here represents a payoff for the two firms which are competing in a dynamic environment. Both axes Y and X they are the expected profits from a particular strategy or from a particular equilibrium, I should say. And a very nicely defined diagonal here shows the maximum profit that can be earned on this market by a monopolist. And you can see here that some dots are situated right in the corners. So that corresponds to the situation where one firm extracts all of the profit as if it was a monopolist in some particular equilibrium, whereas the other firm has zero. But I wanted to talk about the size and the color. So we're using, as you can see, both the size and the color in this plot to visualize two additional dimensions of these equilibria. I believe the color here shows how many times a particular point is actually listed in the full list of equilibria, and you can see some of them are quite popular, whereas the majority of the equilibria are not repeated. All right, now let's talk a little bit about the visual debugging and dashboards. I find this very, very useful in the projects that I work with. And what I mean is that sometimes drawing a plot of the intermediate results of your code allows you to actually see whether the code works or not, and to find errors in the code. Going back to this plot, for example, initially we would get an equilibrium in this white area, the upper area of the diagram, and from economic standpoint, that wouldn't make any sense, because we could calculate the maximum profit that can be earned on the market, given the demand system, by a monopolist, and it's impossible for a duopoly, which we're picturing here, to earn collectively something more. So, when we had dots in this upper triangle, it was very clear indication that there was a problem with the code. Here's another example. These are simulated wealth paths in a consumption savings model, a life cycle model. And in this particular example, the length of life is 25 units of time. And we know from the theoretical properties of the model that everybody should spend down their wealth exactly by the time they die. There's no randomness in the length of life in this formulation. Now, we've simulated many different initial conditions, as can be seen from this left side of the graph, and many different sequence of shocks in this model. And you can see that everybody comes to exactly the same point towards the end of their life. And that tells us that the solver of this model works correctly. So the analytical property of this model is confirmed in the numerical simulations. Now, here's an opposite example. We are drawing a particular function in one other model, which involves continuous and discrete choices. And depending on the number of points that we use to discretize a particular object, you can see the appearance of this strange discontinuity points, like over here, for example, between the square dots. It's not necessarily a problem. It was the problem of the numerical approach rather than the code itself. But it is very visible once you draw these points and look at them as a line, that there are some noise in this function that we are trying to calculate. Now, going to the dashboards. Dashboards is something that I refer to as large collections of plots, which are usually diagnostic plots for a particular problem. And here you can see a dashboard for the life cycle consumption and savings and labor supply model that I was working on. And all it is essentially, you simulate the data. This is simulated data from the model given a solution to visualize what the model actually does. And because an economic model can be quite involved and produce many different variables that you want to control all in the same time. Then putting together this dashboard with different gauges, different plots, would allow you to see the big picture and to think about where the code may or may not be working correctly, or where the model is working correctly for that matter. Maybe sometimes you see something like this jump over here, for example, that has to do with superannuation being paid out at 36. Maybe you didn't expect that, okay? And maybe you can think of how to think and reorganize the model. Now, if you want to match your simulated data or your numerical model to the data, dashboards are also extremely useful. So here you can see several variables drawn over the life cycle. Again, this is a dynamic model, and the simulation is always the red line, whereas the black line with a little shadow around it is the data that we want to match with the model that we're working with here. And there are different variables which are simulated over the life cycle. For example, whether household works, their wage, their hours of labor supply, things like that, their wealth. And we are trying to find parameters in the model such that all of these graphs simultaneously sort of start matching up with the data. And to have this big picture of where the model performs worse or better, it is really, really useful to build these dashboards which contain many different plots. I guess that's what I wanted to say about using visualizations for the solutions. But sort of more fundamentally, it's very important to plot the implications of the solutions of the numerical models for just making new insights in the theory and into our knowledge. So here, for example, I'm plotting two best response functions in a particular model of a dynamic competition. And it came quite as a surprise that with in the particular points in the state space, with particular parameterizations, it could be that we have 5 equilibria in this game for a particular stage, as I said. And the way to see that very visually and very clearly is to essentially just plot the best response functions for firm 1 in green here and for firm 2 in red. And you can see there are 5 intersection points of the best response functions. Something that would be that wouldn't be straightforward to guess by just looking at the equations. And of course, if you're unaware of the possibility of multiple equilibria and employ a numerical procedure, say an equation solver, to find a solution, the intersection point, it could be that you find one out of many, and then which one you find is totally dependent on how the numerical procedure is organized, rather than economic considerations of maybe one of them should be used rather than the other, or maybe all of them should be analyzed. So here's an example of where plotting the inner workings of the model led to new theoretical insights about this model. And here's a continuation or generalization of the previous plot. So in color here, so I'm using color, I'm changing one of the crucial parameters of the model, which actually affects the number of equilibria. And this is a crude graph. This is probably not for presentation or the paper. This is to get some intuition into what happens with the model as we change this parameter. You can see that when parameter is low, the sigma, we have multiple equilibria in dark blue. But as it goes into the intermediate levels, it seems that there's only 1 point or maybe 2 points which are sort of greenish here. And then as it becomes very large, then again we have 2 or 3 even. And what's plotted here are these equilibrium points and how they move around within the space of choice probabilities, right? So the space is nicely bounded to a unit square. So again, this plot shows that, drawing the solutions as parameter changes, this is what may be a very useful tool in understanding the theoretical properties of the model. Finally, a couple of graphs about the equilibria in the dynamic competition model. Out of all of the equilibria, it's a similar plot that what we've seen before. Here we are highlighting the equilibria which only involve pure strategies. And we're making a statement in the paper that the closer the equilibrium outcome, the payoff is to this diagonal, the more efficient it is because the resources are not wasted. And you can see very clearly from this plot that the equilibria which involve pure strategies only, they are more efficient than all of the equilibria which may involve playing mixed strategies at some points of the game. And it's the mixing or mixed strategies is what drives the inefficiency in this model. And this is another example of a theoretical insight that you can get just from visualization of the solution of a numerical model. Here's another example from the same paper. Here we highlight the equilibria which correspond to a quite common symmetry assumption, which is made in the literature often. And you can see that the symmetric equilibria is only a small fraction of all of the equilibria that exist in this model if you relax that assumption. And in particular, they are of very particular type, right? This mixed equilibria, they're all sort of close to the origin. They're very far away from the efficiency frontier. And yet, if you don't know about that, then the assumption you're making could be very, very limiting. All right, so let me stop here. And in your weekly exercise, there will be questions that are coming as part of this tutorial on Matlablib, which asks you to do the nitty-gritty of the using of the library. And I also really require you to look at this presentation by Hans Rosling, who is which is a real joy to see in how he is using visualization to drive his point across. Among the additional learning resources, you can see this wonderful tutorial on Matlablib given by the authors. It's kind of long, but you can speed up the video if you really want to dive deep and learn the deeper details of this library. And here's a nice example of this visualization of the sorting algorithms, which shows you how visualization really allow you to get an understanding of how different things work, in particular sorting algorithms. All right, see you next time.